So next journal paper award winner is the paper titled Evaluation Measures of Individual Item Fairness for Recommender Systems, a Critical Study. And to present the work, Theresia, Veronika, Rampisela is here. Welcome.
Hi everyone, my name is Theresia and I'm a PhD student at the University of Copenhagen. So today I'm going to talk about evaluation measures for individual item fairness in recommender systems, but more specifically about their theoretical limitations and how we try to resolve some of the limitations. And even though this paper has plenty of equations, we will try to keep the maths to a minimum for this talk. To give some context about individual item fairness, here is an example. Suppose we want to recommend 2 items from a pool of 4 items to 2 users, and here are the items in the dataset. In the first case, only 3 out of 4 unique items are recommended or exposed, but in the second one, all 4 items are exposed. So based on existing fairness definition for individual items, where fairness is defined as all items having equal exposure, we can say that case 2 is fairer than case 1, because there are more unique items that are exposed in the second case. But why should we care about this type of fairness in the first place? Well, imagine if the items here are job applicants, or maybe the content or posts that we have created on social media. Or perhaps this could be our research papers. So these are just some examples where providing exposure is important. Now when we talk about evaluation measures of fairness, there are 2 important goals of this type of measures. The first one is to compare different models. So basically, is the recommendation from model A fairer than model B? And the second one is to quantify how fair the recommendation from a model is. So here we want to assess models in isolation, where one endpoint of the score range being mapped to the most unfair case, and the other being mapped to the fairest recommendation scenario. What we did in this work was to take 9 existing fairness measures. We identified 5 limitations in them, and we resolved 3 of the limitations. And here are the 5 limitations. So first we have the undefinedness limitation, where a measure cannot be computed due to, for example, computing log 0. Then we have the non-realizability limitation, where the measure cannot reach the maximum or minimum score for a few reasons. Then the third one is the always fair limitation, where the measure just gives the fairest score regardless of the recommended items under a specific constraint. Then there's also quantity insensitivity, where the item frequency is ignored, and also item representation dependence, where depending on how the items are represented, the fairness score can change. Due to the limited time, we will only focus on the first 3 limitations, which are the more serious ones. So we will explain the limitations through some examples. So suppose we have these 3 items, and we want to fill these 2 slots in the fairest possible way. And let's say we fill it with these 2 items. But then the thermos here is not recommended. One measure is not defined to handle cases like this, where an item has 0 exposure. So here, the measure will give an undefined score because log 0 is undefined. And to correct this, the solution is pretty simple actually. We only compute the log sum on the recommended items. Then the second one is the non-realizability limitation. This happens because no matter how we try to fill the last slot, we cannot make each item to be recommended exactly the same amount. So let's say we fill this in anyway, and we compute this measure called Jane index. And here the Jane index is only 0.89, while in theory, the maximum amount or the maximum score for this measure is supposed to be 1. So then there is an interpretation issue here because the measure does not reach the fairest value. even though we cannot have a fairer recommendation than this. So how did we correct this measure then? So for Jane's index, here's the original equation. And the actual equation here is not very important, but here are some details if you are interested. And basically, we correct the Jane's index through min-max normalization so that it resolves the non-realizability limitation. And we take the maximum score here as the fairest possible score, which we get by recommending the items such that they receive exposure as equal as possible. And then we take the minimum score from the unfairest possible score, which we get by recommending the same items, k items, to all the users. Next, we have the always fair limitation. This happens when there are fewer slots than items. And if we compute the measure f set on this recommendation, the score will be 1, which is the fairest, even though there is arguably a fair recommendation for this. So here is the fair recommendation. And in this case, we would say that the measure is unusable because it will just keep giving the fairest score, which is 1 for any possible combinations. Finally, we also conducted some experiments to compare the corrected measures against the original measures. The colors here refer to the different fairness measures, and all of these measures should range between 0 and 1, theoretically. The crosses refer to the original measures, and the circles are the corrected ones. So the first question that we are trying to answer here is that given the fairest recommendation, can these measures reach 1? And the answer to this is that our corrected measures can always reach 1, but the original measures, they sometimes cannot do that. The second question is a bit of the opposite. Given the unfairest recommendation, can the measures reach a score of 0? Well, our corrected measures almost always can, except for one case where we cannot fix the limitation, but the original measures, they are never able to do that. So to summarize, there are two main things that we can learn from this. First, we should use the original measures to evaluate relative fairness. So this is where we care about the ordering of fairness scores from different models. But when we want to evaluate how close a recommendation is to the fairest recommendation scenario, then we should use the corrected measures to evaluate it. So for more details, we refer to the full paper. And we also have a follow-up paper at SIGIR this year, where we investigate fairness measures that consider fairness exposure with respect to relevance. And we also look at the empirical tendencies of these measures. That's all from me. Thank you for your attention.
Thank you very much. And congratulations again. Let's see, we still have 1 minute for questions, and I see a lot of questions, so maybe you have to check Slido afterwards. But I will just read one question. Why should we aim for equal item exposure? If some items are lower quality, it's unfair to recommend them, as users shouldn't get bad items. Shouldn't fairness consider both item and user perspectives?
Yes, this is a very interesting question. So I think the answer to this is that it's inherently difficult to infer the quality or the value of item beforehand. So at least we can measure exposure separately first before we incorporate relevance. And in the follow-up paper, also when we try to, measure fairness with respect to item relevance, we found that these other measures also have limitations, and it is better to measure exposure separately first from relevance. But in the future, maybe it's also a good thing if we can measure both at the same time.
Yes, thank you. Yeah, please remember to check Slido, and also the audience, you could also talk in the break, maybe after the sessions. Thank you. So next.